a small introduction.
I have begun the recording.
Okay. So, hello everybody, my name is Damir Farizovic and welcome to another installation of the point distributions webinar. Our guest tonight is Stefan Steinerberger, and he will be talking about optimal transport and point distributions on the torus. So please, Stefan.
Thank you. So I've actually never given a talk on this, not in that form, and so it's the first time I'm sort of giving the right talk to the right audience. And I'm very happy that Dima is here, because I remember 2 years ago I talked to Dima and I said, you know, this Wasserstein Distance somehow seems useful. So I'll give you basically a very broad overview of things that I and Louis Brown sort of managed to do, and there's a lot more problems waiting, and it's sort of a very interesting alternative perspective on uniform distribution. But there's a lot of parallels, which makes it very interesting. So I'll give you the shortest 2 slides of high-level overview. So the question is, how do you distribute points regularly, say, on the unit cube, right? How do you, or sequences or sets, right? That's sort of the question, and there's a certain duality there. But that's sort of a very old question and very well studied. And there's a classical notion, and that's discrepancy. And everybody likes discrepancy. And I'll define it later at some point when I need it. This is very high level. Discrepancy is sort of the maximum deviation within small boxes, rectangular boxes, and there's 2 reasons why people like it, I think. Number 1 is it's geometrically meaningful. Like, it tells you a great story. And number 2, it actually, you can sort of, you know, you can write in ground applications that it's, you know, you're actually doing numerical integration, right? Because you help solve all sorts of applied problems, because there's the Cox-Malavka inequality, which says that if you sort of approximate an integral by a sample and endpoints, you can bound the error by the discrepancy and the total variation. And here, this is the discrepancy, which is just a property of the points, and that's total variation, which is a property of the function, right? And that's what I learned in undergrad. I studied in Linz, that's why I learned this in undergrad. I don't think there's many places where you learn this in undergrad. But, and as I said, the story seems sort of believable, but after, you know, I don't think it holds up, because if you want to actually do integration, because Hardy-Krause doesn't actually like work, right? I mean, it tends to grow exponentially for any sort of interesting function in the dimension. So I don't think you can actually use this inequality on nonlinear functions in dimension 10. Like, I don't think it's ever reasonable. But that's sort of the official story, is that's sort of why the discrepancy is good. And what I'm proposing is, I'm proposing to look at a different object. And I'm not saying that it replaces discrepancy. I think it might lead to a different story that might be also interesting. And I'll define this later. I'll define it in great detail, but it's another notion of regularity. It will be geometrically meaningful because it actually comes out of economics, where it's about transporting mail, if you want. And it's also connected to practical applications via an inequality, which happens to be not Cox-Malavka, but it's Kantorowicz-Rubinstein. And it looks like this. So you get a similar kind of inequality, and what you get is you don't get total variation, you just get the Lipschitz constant, and you get this transport distance. So the same story is there, right? The same motivation is there. This inequality is actually sharp, so the constant in front is 1, which is nice, and that's sort of Rubinstein. And I would also argue that the Lipschitz constant is a lot nicer than Hardy-Krause, which is higher order derivatives. I mean, it's 2 different problems if you want, right? But Lipschitz is sort of a nice setting. And okay, so I should preface this as follows. Okay, I'll say this after the slide. So, but suppose you want to sample a function in a 100-dimensional unit cube, then discrepancy, you know, can be something like this. There are point sets for which this is attained. But this function is actually increasing until you hit e to the 100. So you're not going to get any useful bounds out of Cox-Malavka. Cox-Malavka is never going to be applicable in practice in high dimensions. This is applicable. There is no constant that grows. The Lipschitz constant is the Lipschitz constant. The price that you pay is that this object does not decay quite as quickly. So this decays quite slowly, as you can see. And in 100 dimensions, you could also argue this is not going to be feasible. And I think the underlying truth is the following. In both cases, the bound is the bound. The bound is not great because numerical integration is hard, especially in high dimensions. But in both cases, the object in front does indicate an interesting object that maybe one wants to minimize. And in discrepancy, it's the beautiful 100 years of theory of discrepancy theory. It leads to gorgeous results. And my question is, what sort of results can you get here? Can it be interesting? Okay, so that's sort of the rough outline. And I'll tell you in great detail what is optimal transport, and I really won't. So 3 years ago, I tried to say, as I said, maybe I should learn this optimal transport. Everybody's doing it. So I looked at it, and I got this big book by Villani, and I think I made it through the first 5 or 10 pages, which is the Wasserstein distance. And then I said, okay, what's the Wasserstein distance of point sets, right? That's something I sort of know, and I never really went back to the book. So I know nothing about optimal transport, but I can tell you what the Wasserstein distance is. And then I'll compute it for some classical objects. So in particular, maybe one should go back to the book and learn more, right? Maybe it's helpful. So I'll compute it for some classical sequences, which is very nice because it's not an abstract notion up in the air. You can actually compute it. And there are various ways of computing it, and recently a lot more ways were developed. So I think this is actually, you can touch it. It's not abstract. And then I'll tell you what this means for numerical integration. And there'll be a lot of problems interspersed, and usually 5 people may have thought about the problem. So there's a lot of room to do things. And feel free to interrupt me at any point in time. Okay, so Wasserstein's funny. Wasserstein distance, optimal transport. So the theory goes back to Monge and Kantorowicz. Those are usually cited as the originators of the theory. And he has a sort of, I never found the actual text, but I think it's something about like, how do you move Earth around, right? You have Earth on the ground and you want to move it somewhere else, how do you do it? Or the problem that's often cited is you have coal mines in France, and then you have the people. But the people are in Paris, or many people are in Paris, and the coal mines are not in Paris. So which coal mine sends the coals to Paris and which sends them to Toulouse, and what's the best way to sort of arrange this? And the second part of the story is Kantorowicz. So I found something funny to introduce him. I found the CIA file that they had on him, which was stolen from the US Embassy in Tehran. Now you wonder which sort of friends do I have? It's on Wikipedia, okay, for the NSA. I'm boring, my friends are boring, it's on Wikipedia. Here's the file. So that's pretty cool, right? If the CIA has a file on you and it says an internationally recognized creative genius, that's pretty badass. So Kantorowicz, very smart guy, and he sort of is, if you want the Russian John von Neumann, he worked on all sorts of functional analysis and then also optimal transport. He was actually an economist, and he did win the Nobel Prize in economics. So, and I think a Lenin Prize or Stalin Prize, which is also hard to do, but it doesn't sound as good. So I'll give you the 5-page introduction. Okay, the first 5 pages of optimal transport, and for all subsequent purposes, the measure mu for me is always going to be the empirical measure. So you put a Dirac in each point of a finite set of points, and nu for me is always going to be the Lebesgue measure. Okay, so this is going to be very straightforward. But the idea is you have sort of 2 measures, and this is expertly drawn here, right? You have the blue Earth, and the red is the same amount of Earth, but how it should look like, right? So this is the thing you have in your garden. And then someone comes and says, you have to move the Earth over here. How do you do it? What's the cheapest way of doing it, right? So the question is, how do you assign a cost to such a process? And the way to do this is very straightforward. It's the physical cost. So think of this Earth as little boxes, and each box has weight epsilon. And I'm telling you that the cost of moving a box of weight epsilon, distance delta, is epsilon times delta. So this makes sense, right? If I move 1 pound 1 mile, it's half as expensive if I move 1 pound 2 miles. Right? I think that's actually the physical cost. Like if I were to carry this would be caloric expense if you want. Or if these are warehouses and then trucks deliver it to the people who order stuff from warehouses, right? That would actually be the miles times weight driven. So it's the actual physical cost. So I'll give you an example, right? Suppose you have 1 unit of mass in 0, that's blue, and then you want to transport it to the red measure. The red measure has 1/3 mass in A and 2/3 mass in B. Then what's the cost? Well, I have to transport 1/3 of the mass distance A and I have to transport 2/3 of the mass distance B. That's the cost. And now you know the definition of the Wasserstein 1 distance or the Earth mover distance. I don't see the chat. If anyone wants to ask questions, sorry, I never figured this out. Maybe just unmute yourself.
We'll let you. We can also let you know if there are any questions in the chat.
Great. So there's also an LP version of this, which makes things very interesting. And you should think of the WT Wasserstein distance as sort of, it behaves a little bit like LP. So as P goes up, it gets bigger. And there's sort of different types of behavior. And I'll just tell you what happens in this example, and you see immediately what it is. You basically take P powers of the distance. You don't affect the mass that you transport, and then you take a 1 over P through it. So for the purpose of this talk, if you want to just always think about W1, that's probably the best thing to do, right? Everything is interesting for W1. W1 is sort of the physical thing that makes sense. I will state many results for W2, which is a larger quantity. So I'll bound W1 from above by W2, and then I'll use bounds on W2. But that gives you bounds on W1 as well, which is the natural object. So here's another example. Suppose you have 1 unit of mass in 1/2. So there's 1 Dirac sitting right in the middle of the interval. And you want to transport it to the interval. So what is that? Well, you just write it out. So you have to compute a little bit of mass to each point. So the average cost is the average distance to 1/2. And that's 1/4. And the WP distance would be this. And you see it's a bit bigger. And in general, WP is always bigger than W1. And for this talk, again, I emphasize, make everything W1 with just a nice Earth mover distance. Okay. Okay, any questions on this? Okay, so this is, it's really just, how, you know, imagine yourself on the unit interval and you have to carry the little masses around. How far do you have to carry them? That's it. And so here's an example, right? Suppose I have the quadratic residues in F29. So I take the field on 29 elements, 0 up to 28. I look at, I take each element and square it, and that gives me half the field. Half the field has solutions of x squared is that number, right? So those are the quadratic residues. They're actually here, right? Because 1 squared is 1, minus 1 squared is 1, 2 squared is 4, and so on. And this is how they're distributed on the unit interval. And 0 only appears once, whereas the other ones appear twice because there's x and there's minus x. That are 2 solutions to the same equation. So what I've given you is I've given you a probability measure on the unit interval coming from the quadratic residues. And now you could ask yourself, you know, what's the cost of transporting this? And what's funny about this notion is you can actually compute these things, or you can bound them at least. So in general, the computation of Wasserstein distances is very hard. It's a computationally very challenging problem, but bounding it is not. So I'll give you a theorem, and the theorem says that if you have a prime field and you look at the quadratic residues of the field, so that's k squared mod p, and then you scale it down to be in the unit interval, then the transport cost, transporting this to 1 over square p, to the uniform measure, is 1 over square p. And it turns out that's essentially the same scaling as you get for random points. And this actually confirms one of the very nice heuristics in number theory, which say that quadratic residues roughly behave like randomly dropped points. It's not true, right? Because for any finite field, there's a deterministic set of residues. But with respect to sort of abstract statistics, a good intuition is to assume that they behave randomly. So it also tells you that an average particle has to be transported 1 over square p distance to the uniform distribution. And I'll tell you in a bit how to compute this very easily, but we can compare it to the discrepancy. Now I'm sort of introducing the discrepancy once and for all, right? It's on the unit interval. It's you take all subintervals and see whether there are too many or not enough points, and you compare these relative proportions. So there are 2 theorems for this particular set, the set of quadratic residues in a finite field. And what they tell you is that the discrepancy is roughly something like 1 over square p. But there's a logarithmic correction, or if you assume the generalized Riemann hypothesis, a doubly logarithmic correction. Now, I would argue that the discrepancy is a more subtle notion, right? Because it's the deviation over the worst interval. It's sort of, it's a subtle object. Whereas the average transport sort of doesn't care too much about a single outlier, right? If you have a single particle that is far away from everyone else, if it's not typical, then it doesn't probably matter all that much. So I think of these Wasserstein distances as sort of average, smoothed out discrepancy notions, if you want. But also, it's a lot easier to prove stuff. Like this is a non-trivial result, and this is presumably a fairly non-trivial result, given that it's using generalized Riemann. Whereas my proof is half a page, and I'll show you the half a page. later. It's going to be very easy. It's plug and play. So actually, this was improved by Cole Graham, who showed that you can actually increase the value here. It doesn't have to be 2. It can go all the way up to infinity. And it's still 1 over square root p. And then at infinity, you actually have to have a logarithmic correction. Like something, W infinity like is something like discrepancy, right? It's the furthest you have to transport. And he also pointed out that there's actually a nice identity that gives you that the W2 distance is at least 1 over square root 12p. So it shows that my bound is sharp. It also shows that all his bounds are sharp to constants. That's sort of nice. So what I'm saying here is that there is a notion of regularity of points that is connected with, numerical integration in just the same way as Cox-Malavka, that tells you how regular points are. And that is computable, or at least it's not, I can define many notions of regularity and I can't compute a single one. This one I can compute, in some cases at least. Just as discrepancy is a very hard notion to bound for even these sort of objects, it requires a lot of work. This one is using existing technology and existing bounds. So here's another case, which is a Kronecker sequence. So you use, a badly approximable number, maybe square root 2, and you take these multiples and you put them on the unit interval, unit circle. Then this N alpha sequence or Kronecker sequence is known to be highly regular, and you can bound the W2 distance by a square root log n of n.
Sorry to interrupt just real quickly, because it's been a little while since I've dealt with that. Can you remind me what badly approximable means?
Oh, sorry. Badly approximable means a bounded continued fraction expansion. It means that it's an irrational number such that no rational number is too close. It's the things for which the Dirichlet approximation theorem is sharp.
Thank you.
And it's not very important. I'm writing a square root 2. In the proof at some point you need it, but that's okay. The important thing is that you can save a square root. So discrepancy is log n over n. Here you actually save a square root log n, which is pretty nice. And then the natural question is whether this is best possible. And Cole Graham in the same paper proved that in fact it is best possible. So there's the irregularities of distributions principle saying that no matter how you pick your infinite sequence on the unit interval, at some point it's going to be lopsided and it's going to be expensive to transport it to the. So this is the analog of Schmidt's theorem, if you want. Right? Schmidt's theorem from the 70s tells you that discrepancy is always at least log n over n for infinitely many n. Now there is a Wasserstein analog in 1D, which is squared log n over n. Okay. So how do you prove these sort of things? Well, it turns out there is a gorgeous little result that came out not too long ago, which says that if I want to bound the cost of transporting any measure to the flat measure, it can bound it by the norm of the measure in the Sobolev space H minus 1, which is maybe not too familiar, but if you write out the measure as a point measure, this bound just says this. So Poiret gives us a very nice bound that is sort of universally applicable, is super nice, super friendly. And it looks a bit like Erdős-Torán, maybe, right? And it means that for many sequences for which you have these objects sort of understood, you can just plug it in. And this is what I did for the quadratic residues. For the quadratic residues, if you plug it in, this is known as a Gauss sum. And there is an explicit formula for what it is. It's p if your index is divisible by p, otherwise it's 0, something like this, or square root p. Anyway, you just plug it in, and then you have an infinite sum that's not very hard to estimate, and you get the right answer, 1 over square root p. So the proof is nothing, right? It's not really there. And for Kronecker, you can argue sort of, so if you do n alpha, this is also has a nice bound, and you plug that in and you play, and it's not too much work to get the bound squared log n over n. So both these results are actually fairly easy. So a summary up to now is Wasserstein distance gives us another perspective on regularity and irregularity of point sets. And it's cheap to compute, at least when you have exponential sum estimates on the torus. Like when you understand these objects, you get a very nice bound sort of for free. And there are now, there's now more activity on this. So Graham has similar results on the torus for other WP distances, and Borda actually has results like this on compact Lie groups. So it's very nice because it both sort of this abstract notion of the Wasserstein distance from one measure to another, how a point sets, right? It's actually directly related to Fourier analysis, and there is a lot of Fourier analysis that's known. So I think that's sort of why I like this notion. I think it's ready to be analyzed because we now have a lot of tools.
Sorry, in the exponential sum, what's the subscript on the x supposed to be?
K, sorry, xk.
XK. Just checking.
Sorry.
Thank you.
Actually, that mistake seems to be continuing. Sorry about that. So it turns out some people may have recognized this. So this is actually in one dimension known as Zinterhof's diaphony. So there are some results on this. And in particular, since people have studied Zinterhof's diaphony, we immediately get a Wasserstein bond for the van der Koppel sequence as well, from a result of Proinov from the 1980s. Of course, Proinov did not consider Wasserstein, and I'm sure maybe, it didn't matter, but he bounded this for the van der Koppel sequence. We know it bounds the Wasserstein distance, so we get the optimal result for Wasserstein also for van der Koppel. Okay, so van der Koppel, Kronecker are all optimal. I assume many others are optimal as well. Okay, so now irregularities of distributions. So now the question is what happens in higher dimensions, right? Because in the classical discrepancy notion, this is the hard problem. And I like to think of this as a fun problem regarding coffee shops, right? Because, so suppose you live in a square town and you want to open up a coffee shop. Then you want to open up your coffee shop in a fairly central location. So you want to put it sort of in the center of the square, right? But if you think, in terms of expansion, right? At some point you want to open a second coffee shop. And that's, if the center's already taken, you have to sort of put it on the fringe. So how do you put the coffee shops so that they're always central? So in particular, if someone tells you open 9 coffee shops in a square city, right? You've placed them like this. Because the transport cost, right? The Wasserstein cost of the Dirac measures to the flat distribution is actually the average distance that a customer has to walk. Right? If you walk around in your city and you get sort of thirsty for coffee at random intervals, you pull out your phone, you find the next coffee shop, you go there, which means that the average walking time through a coffee shop is actually the Wasserstein distance. And you want to minimize that. Right? So if I want to open a coffee shop, right? And of course I want people to go to my coffee shop. So if I know in advance I'm going to have 9 coffee shops for the rest of my life, this is how I would arrange them. But if the 9 coffee shops go well, I want to put a 10th one. Right? And the 10th one, where do I put it, right? None of them are particularly good, right? If I put it somewhere, maybe here, right? Then where do I put the 11th one? Or the 12th? How do you actually do this, right? So that's sort of the sequence problem. So the question is there a sequence on the unit square such that uniformly for all n, this is always bounded by 1 over squared n? And that's a coffee shop problem. And how do you do it? Right? And that's actually a real life problem. I mean, okay. For the purposes of math, it's a real life problem. We have Graham's result on the unit interval saying it's impossible. On the unit interval, at some point, you will lose a square root of a log. You will have to. But what about 2 dimensions? And it turns out you can actually do this. So there's a nice construction which says if you take a badly approximable vector, which basically they're vectors in R2 with the property that all the multiples are far away from all lattice points. And they're fairly non-trivial objects. I think their existence is only done in the 20s. And it's one of these instances where you don't have continued fraction expansion in higher dimensions, so everything's really hard. But they exist. And if you take one of them and then take the multiples and wrap it around the torus, then in fact, you get this optimal rate. So there is a solution to the coffee shop problem. However, and I think as the dimension gets higher, the problem actually becomes easier, which is sort of an interesting phenomenon that I'll talk about later. But I think the 2-dimensional problem in some sense is the hardest. And so the question, one interesting open question that I'd like to see is how frequent is this property? And don't focus on the 2. If you can prove it for W2, that would be nice. But W1 would also be interesting, and W8 would also be interesting. Like anything in this direction would be interesting. So how easy is it to solve this coffee shop problem? If you put a Hammersley sequence or a Halton sequence or anything like this, is it easy? Do they generically do low discrepancy sequences on the unit square have this property? I don't know. Like this construction is certainly very, very sensitive and it's very subtle and the estimates are quite delicate, but it might just be that we have the wrong estimates, right? That we proceed in a suboptimal way, and that's why it's hard. Maybe generic points are fairly good at this. If you take random points, you lose a log. And that's actually, so I don't have a slide on this, but there is actually a series of results that go back to Dudley from the 60s, and then there is Aitai, Komlosh, and Tusnadi, who have a combinatorial version of this. And then there's Ledoux and Bobkov, who have yet another version on this. So the stochastic world has this analyzed. But the discrete, like for low discrepancy sequences, this is not, I don't know any results except this one. So I think this is quite interesting. And it's interesting in all dimensions, but I think the two-dimensional case may actually be the hardest. Okay, so, yeah.
Quick question. Could you repeat what exactly you assume about the vector alpha here?
That it's badly approximable vector. So what this means is, it means that if I take alpha times n being an integer, then the distance to any lattice point is at least 1 over n squared. That's the scaling, I think. So it's the analog of badly approximable number. And essentially what we have is we have these kind of, when we do the Fourier analysis, we have 1 over inner product of alpha against a lattice point, and we want that to not be too small for lattice points that are small. So the proof is not, like if you've ever seen a proof of Kronecker sequences, this is very similar. The proof's not the issue. The issue is, are there better constructions? How do you deal with this? So okay, how do we deal with this, right? So I'll tell you how we deal with this. It turns out Poiret's estimate, which says this is bounded from above by a Sobolev space, is completely accurate. It's completely true. But Dirac measures are no longer in that Sobolev space once you're in dimension 2 and higher. So Poiret's estimate is great in 1 dimension, and it just works, and it's gorgeous. The moment we're in 2 dimensions or higher dimensions, we can plug it in, but the right-hand side is infinity. So what we'll have to do, so this is actually the same in Zinterhoff's diaphony. If you look at Zinterhoff's diaphony, I don't think it has ever been generalized to higher dimensions because it doesn't, the sums don't converge. So I've had this before, right? So I don't think it's been generalized to high dimensions because it's a great object in 1D. It has been studied in 1D, but never in high dimensions because if you write this sum out, things don't converge quickly enough, right? This sum does not go to 0, right? This is somewhere like squared n. I mean, it can't be too small all the time. This thing forces it to be small. But once you have more lattice points, things are different. So I think of this actually as sort of a generalization of Zinterhoff, if you want. So here's what we do. We use the triangle inequality. That's also the first 5 pages of Villani. Wasserstein distances have a triangle inequality. And physically it makes sense, right? You put your pile here and then you put it there. That's certainly more work than putting it from here to there. So what we do is we put an intermediate measure here. And we pick the measure so that this is fairly, we smooth out the Diracs. We make them little Gaussians, essentially. Then we can sort of bound this by hand. And once the little Gaussians, that's a nice measure, and the nice measure is in h-1, and we can use Poiret's estimate on this. And when we do this, we get this estimate. So this estimate is, if you want to think, this is actually, it looks like Erdős-Turan, right? You have the 1 over n here. And then you have a sum that depends on this value n, how far you go. This is an Erdős-Turan type object. You have to balance 2 factors, and this is just a real number. That's positive. And the larger this real number, the more you have exponential decay on high Fourier frequencies, and that forces the sum to converge. So now we have Erdős-Turan. Right, so in particular, I can now have an upper in any dimension on the nice torus. I can give you a Erdős-Turan type bound for the Wasserstein distance. The question is, how small can you make this for nice constructions, for nice sets? I don't know. We did it. This is what we used for Kronecker, right? For the Kronecker argument, we just use this. We bounded this via the sum standard. This becomes a geometric sum, and then we just balance the t. But this should also work for other sequences. It should work for other sets. Well, I don't know what can be done on this. So in particular, I think having these sort of inequalities and also the Graham and Borda, right? There's other inequalities now out there. I think it would be interesting to actually study classical objects and sort of make sure that they have at least the optimal Wasserstein scaling. So in particular, what about Halton sequence, right? What about the Hammersley set? Sobol. Then I think TMS nets might actually be sort of, there might even be a direct argument because they say that the mass is sort of nicely balanced in all cubes, right? So there's a lot of that's known about them. So I think there might be sort of, you might be able to write directly that this point is transported to this square, this point, that there might be an explicit construction. And I would argue that many of these objects should actually satisfy this bound, both in 2 dimensions and higher. And I think the analog of low discrepancy sequence is satisfying this. And this is what can be said. And in particular, some of them, surely there must be some exponential sum estimates that work. Maybe there's some explicit constructions. Maybe, maybe this way of smoothing is not the ideal way, right? So this gives us, we use a Gaussian, we go from a point measure to a Gaussian, but you could go to other objects as well, right? You could replace each point measure by a little sort of tent function, which is nicer here, maybe a bit slower here, but maybe it doesn't matter. Or you could use it, you could replace it, you could transport the sort of stuff that's compactly supported on the Fourier side, so this sum becomes finite. It's not clear to me. It's just not clear to me. Okay, here's another question, right? So in the standard setting, you have discrepancy, right? And then you have Cox-Malawka. I think we have this. But what if the function is twice differentiable, right? If I tell you the function is twice differentiable and there's a bound on the second derivative, can you use Wasserstein notions to get similar types of estimates? So in particular, recall that for the classical discrepancy notion, there's a 1 over n decay. But the 1 over n decay actually comes at a cost, right? The cost is that the function has to be at least t times differentiable, and the derivative, the size of the derivatives goes straight in the Hardy-Crowder variation. So what happens if you actually do this, and you're not going to get such a nice duality statement, but how do things depend on this, right? Is this a notion of regularity that goes through to higher regularity of integration? That would be an interesting problem. So this in particular, right? So it's known, this is one of my favorite questions. It's known that discrepancy scales like this, and it's also known that the constants here are absolutely evil, right? They're way too large. So this has been dealt with, right? So there is a result that says there is a set of points such that if I have 15 points in 800 dimensions, maybe that's a bad example. If I have 800 points in 15 dimensions, I can still get something fairly reasonable. It's not at the scale of 1 over n or log n over n, but it has a nice explicit constant. And you can pick, the constant's not gigantic, right? So there are explicit constructions, and these points are chosen randomly. So random points have this. As it turns out, we have the same kind of problem. So if I want to put n points in the unit square, it's not terribly difficult to get a bound like this. It's not terribly difficult to show that something like this is also roughly sharp. Like this problem actually becomes a lot easier than discrepancy. But again, this is only true as n goes to infinity. So if you have n as 1,000, this is just not going to be true. Like this as n goes to infinity is crucial in the construction. If you just have 1,000 points, I don't know how to make this small. So it's exactly the same problem as the inverse of the star discrepancy, right? The result on the prior slide. If I have 1,000 points in 20 dimensions, it's not clear what to do. And it's not clear how small this thing is going to be. So in particular, I mean, when as n goes to infinity, I assume that lattice structures are going to be optimal. And maybe the lattice structures that give you optimal sphere packing are sort of the best ones, right? That's not unreasonable to assume, even though that's at the scale of constants. But when you have 1,000 points in 30 dimensions, you don't have enough points to get to anything close to a lattice structure, right? It's far away, like 2 to the 30 would be the smallest lattice, right? It's a lot bigger than 1,000. So this is a very serious restriction. And I think it's a fantastic question to say, can you get a result that's worse than this, but smaller than square root d, right? Square root d is the distance between the endpoints in the unit cube. So it's at most square root d. What can you do? You're not going to get this, but what can you get? And which constructions get it? And how do random points behave, right? I don't know whether random points are even good, right? I mean, random points are going to be good if the p is very small, probably. Once p gets bigger, depending on the dimension, random points are not going to be that good either, right? So what can be done? And I'll give you a final application of all of this that came as a complete surprise. It was just playing with these things, and this came out as an absolute surprise, and I think it's quite fun. So the problem of optimal integration of Lipschitz functions is actually known, and it's known since the 50s. So if I have a point, a function in the d-dimensional unit cube, and I want points such that this is true, that these points exist. Okay, you get the optimal rate n to the 1 over d, you get dependence on the Lipschitz constant, and in particular, if you don't make any further assumptions about the function, this is optimal. And the way to see this optimal is you take this the minimal distance to any point. So in particular, this is going to be 0. This is the average distance, the average smallest distance to a point. And you should show this is 1. And you can show very clear, you can show relatively easily that the average distance to, the average minimal distance scales like 1 over n to the 1 over d. You just put little balls around your points and say most of the mass is outside these balls, and that's sort of how you show it. And I think it's even known that this should be square root d. Asymptotically, it should grow like square root d, and it's known that this is optimal. Okay, so this is work of what is it? Bakalov and Sukarev, I think, from the 50s, the 70s. This is sort of all classical. And in particular, there are results so in particular, there's also recent results by Hinrichs, Novak, Ulrich, all of which say something like product rules are optimal for various smoothness classes. So they have results like this. And this sort of are a good point. So maybe I should take the hexagonal lattice, right? So I didn't try, but that's sort of very good. So what if you want to take a sequence? Okay, so you don't want to take endpoints a priori and sample in those. You want to have a sequence that's uniformly good. And this is actually a real life problem, right? This is, I think I would call it online sampling, or you don't know how many points you get. And this is, you have a supercomputer and you run some numerical integration code, but you're also in the math department and not in the biology department. Wait, this is being recorded, right? Anyway, so someone from the biology department is curing cancer, right? And they ask for computer time. And of course, it cuts your process, right? Because you're computing the optimal constant of, that's fair. I'm happy to have my computer time cut for cancer research. Anyway, so the problem is, if you want to have a code that sort of adapts for this, right? You actually want to have sampling, especially when you do actually sort of finance, right? Because in finance, the problem is each sampling is one solution of a PDE, right? So, which is costly, right? So what you want to do is you want to pick the points in such a way that no matter when the process stops, you have a pretty good estimate in n, uniformly in n. So how can you do that, right? And clearly these sort of point rules are not optimal like this, right? Because when you put the next point, or maybe they are, right? But I guess you can make them optimal, but it's not so clear. So we looked at this, and we found out that if you use the same example for the that you use for the coffee shop problem, which is these multiples of the badly approximable vectors, then you get an online sequence, meaning it's true for all n. Moreover, you get an improvement. This is slightly smaller than the Lipschitz constant. It's the Lipschitz constant and some power that's very close to 1. And then there's a remaining power that's down in L2. Which is fun because this example of Lipschitz integration is actually usually it's considered the optimal easy problem. I think there's at least one textbook that has it on chapter 1 as a problem we can explicitly solve, tractability made easy, right? The easiest tractability problem. But it turns out you can actually improve it. And the reason why this wasn't noticed, I think, is because when you use this maximum growth away function, then this is also 1. So they're both the same size, so you don't notice. But actually, in general, this is sort of slightly better. And so I emphasize this result is true for sequences, not for sets. And it gives you better LP spaces as well. So one natural question is, are there other examples, maybe nicer examples of sequences that give you this? And what we have essentially is we have some sort of, the way our proof works. If you solve the coffee shop problem, you probably get this. So any solution of the coffee shop problem probably gets you a sequence that has this sort of optimal behavior. Okay, and at this point we got curious, right? Because clearly it's a Lipschitz function, right? A Lipschitz function doesn't have any structure. Lipschitz function is just Lipschitz. There's no global structure, there's no global regularity. At every point it's just Lipschitz. So the grid or some lattice like this should actually be best possible. Like I don't think it's going to be I don't think it's a funky sequence that's going to be better than the grid. It's Lipschitz, right? It's sort of local. Everything's local. And so we went back to the grid and we actually managed to improve the grid as well. And we got an L1 instead of an L2. So it's even a little bit better. So the question is, can you get a sequence for which you get L1? That's not a grid. So grid is not sequence, right? It's a set. Can you get a sequence for which this is L1? Maybe the Kronecker sequence even, right? I mean, this badly approximate. I don't know. I honestly don't know. And I'll now do the same thing that people did since the 50s, right? I'll give you an example that is optimal and tell you that this is then clearly the sharp result, right? So it turns out if you pick the old function and you cut it off at a level that's very, very close to 0, and you plug in, you see that this scaling is actually optimal. And you can, but of course, there might yet be another refinement where these spaces are yet slightly improved. Maybe PMO, right? And if you plug in the example, you get the same behavior. So I'm not going to die on the hill saying that this is absolutely sharp, but it's pretty nice. And maybe it's, if someone can put a BMO here, I'd be quite delighted, of course. I mean, that would be cool. But I don't know how sharp it is. Okay, and so Friday is, so this concludes. Maybe, am I early? I think I'm fairly reasonable. In real life, it's 50 minutes. It's never an hour. And I feel myself getting twitchy in the last 10 minutes every time. So maybe I'm okay. One big problem with discrepancy is that it's adapted to the torus, okay? Because you look at the maximum deviation of all axis parallel rectangles. It's not a general notion. It's a discrepancy notion on the torus. Now on the sphere, you can take spherical caps and no one's going to argue with you, but it's not natural, right? I mean, there's no, the problem with discrepancy is what's your discrepancy system? Do you take convex sets? Do you take axis parallel rectangles? And it's certainly not clear what to do in a general manifold. I don't think people have even tried, because you could take balls on the manifold, but then, if the manifold is not nice, then the balls are going to look sort of different everywhere, right? So Wasserstein does not have this. Wasserstein cares about transport. The definition of Wasserstein does not depend on the manifold. It's completely independent of the manifold, which makes this a very, very stable notion. So everything I told you today survives to some extent on a manifold. But of course, the torus is sort of the nicest and the most clearly explicit results. But one big appeal of this entire approach is that you can get sort of uniform results. You can get universal results, and also many other open problems. So on Friday, I'll talk about what happens on the sort of the general manifold case, and that will be more potential theoretic. So right now we have harmonic analysis and number theory, and it's nice. On manifolds, you don't have that anymore. Although I think on the sphere, many of the things are still doable, and they're still going to be very, very nice and very explicit. And I think that's sort of one big thing to tackle would be the sphere with all these things. But on a manifold, there's still very, very nice ideas, many open problems, and it becomes more potential theory. So potential theory becomes the substitute for the harmonic analysis that we lose. Okay. So in particular, I think S2 should be a fantastic object to study, and there are discrepancy notions on S2 that are not spherical cap, and I think this gives you yet another one that is nice. And since spherical harmonics are explicit, right, on the sphere, you actually get very nice Erdős-Turan type statements for Wasserstein. So I think that's pretty cool. And with this, I'm thank you for the attention, and I hope it was fun.
Thank you very much. So please unmute and applaud, or just push the applause button. All right, before we go to the questions, let me perhaps reiterate, Stefan agreed to give a second part of this talk on this Friday at the same time. So we would be happy if you were to join again. And now to the questions. So are there any questions, please?
Hello, so I do have a question.
Please.
So you showed us this Erdős-Turan type inequality on the torus, on the high dimensional torus with the heat kernel smoothing.
Yes.
So I was wondering if you think that's doable for the distance between an arbitrary probability measure and the Lebesgue measure.
Yes. Yes. So I think it's actually funny because people have started doing this sort of all simultaneously. So in particular, Ledoux and Bobkov have a paper where they look at what a combinatorial problem of matching two sets of independent points on the torus, but they use very much the same techniques actually. And in particular, so for any measure, you can replace this. You smooth the measure using the heat kernel or convolving with a Gaussian. The cost of this you can bound because you know how big a Gaussian is and how quickly it decays. And then you have something that you convolve a measure with a Gaussian, so you know how the Fourier coefficients decay. So the Fourier coefficients just get a multiplication of this, right? It's multiplied. So this is just the action of convolving a measure with a kernel. This is the Fourier coefficient of the measure, and the over k squared is the h minus 1 norm. So in particular, you can just, if you replace this here by mu hat k squared, the result remains true for a general measure.
Okay, that's what I thought. I couldn't find the step in your proof where it is actually used that to have.
It isn't. It isn't.
Okay. So the reason I'm asking this is because then you can apply this to study rate of convergence of random walks on the torus.
Yes.
Start with a specific mu, and you consider the convolution powers. And I do have some sharp results for that for W1, but I could not go to p greater than 1. But I think it could be done all the way up to W2.
So this is interesting. So we actually, Francis Su has some results on this from the late 90s. So you have a random walk on a torus, you go randomly left or right, and the step size is square 2.
Only on the circle and for the discrepancy metric.
Exactly. And we tried to get W2 with this method, and we did not get the optimal scaling. We didn't get 1 over square root n. We got 1 over 4th root of n.
Oh, really?
And we think it's that we messed up somewhere.
Okay, so I do have the sharp results for W1.
Oh, that is interesting. I didn't know about this.
Dimensional torus.
I see. Oh, that is nice. Do you have the constant? How it scales in the dimension? So I'll phrase this.
So I only considered like random walks in terms of badly approximable vectors, right?
Right.
And those constants, I think, in the definition of badly approximable are not really effective anyway.
I see. So here's why I'm asking. I'm asking because
other than that, it's effective.
I'm asking because this is exactly the sort of thing I'm sort of highlighting here, right? So there's one fun question, high dimensions, which is how do you do Monte Carlo, right? And right now you pick points randomly. IID, right? But one question is, can you use sort of a random walk construction to get the sets of points that are not as random as purely IID points that need less randomness to be generated, but are equally good, right? Sort of hybrid deterministic random things. Could you send me your paper for W1?
Yes, sure.
Thank you.
Okay, thank you.
Thank you very much. So we have a question in the chat. Okay, about a PDA approach to Ambrosio Trevisan.
That is interesting as well.
Okay, it's a mark. All right, are there perhaps any more questions?
Yeah, I have a question. So I have to apologize, I joined later, so I probably just don't know. It's probably silly, but I don't understand. So why is the expected order n to the minus 1 over d for WP, right? So,
I never mentioned it. Do the following: pick any point, pick an n2 minus 1 over d ball around it with a small constant in front, and compute the volume of the union of these balls. And once the constant is sufficiently small, you realize that the volume is something like less than 1. It's like 1/2, which means half of the unit cube is outside of the balls, which means that you have to transport at least half the measure, at least distance n to the minus 1 over d. That's sort of the argument. So it's not terribly tricky, and it sort of shows why there would be sphere packing involved in optimal lattices maybe, but this is why it's n to the minus 1.
So we are talking, so WP is just the pth Wasserstein distance between the normalized counting measure and the uniform measure, right?
Yes.
Because I am just, so the covering, so you can pick a covering set and you'll get, covering radius n to the minus 1 over d. And when you integrate Wasserstein, you have distance raised to the pth power. So it just,
there's a pth root.
Why it's not
There's a pth root outside the definition.
Okay.
But otherwise you're completely right. Yes,
okay, yes, sorry. But like I said, I missed that part. Thanks.
Yes.
Thank you very much. Are there perhaps more questions?
A question that I had, and maybe this is something you'll be addressing on Friday, is right at the end of the talk, you were saying that the Wasserstein distance doesn't worry about the structure of the manifold you're looking at, which right. So my understanding is right. It has to do with right both mass and like distance you're moving it. Is that? I mean, so does it not depend upon the structure of the manifold in terms of that would somehow determine what your distance function is, or are you always embedding it into some Euclidean space and using Euclidean distance?
No. So I want arguments that are completely manifold dependent, right? But ultimately, Wasserstein is very forgiving, right? Because it's a definition of an infimum, right? It's the best possible plan. So if you make the neighborhood rougher, right, it just adjusts automatically. So it's nice. In particular, on a manifold, right, each point is supposed to transport only short distances.
Mm-hmm.
So you never see the global manifold. You see the local patch around your point, and as there are more and more points, everything becomes sort of Euclidean. So that's why I think that the microstructure is sort of easier to understand than discrepancy, which is completely global, right? It's a harder notion. Of course, if you want to actually put now points on the sphere, that solves the coffee shop problem, which is what I would very much like to see. And there are great constructions of points on the sphere, right? Mm-hmm. How do you actually prove that it has optimal W2 distance? Can you use this Erdős-Turan inequality in some way? These questions are, of course, they depend on the sphere. And in particular, I mean, if you want to use the Erdős-Turan estimate, right, that we have, Erdős-Turan type estimate, where do we have it? Here, you can still get the same estimate on a manifold, except this gets replaced by eigenfunctions of the Laplace, which are just exponentials on the torus, so everything's nice. They're just spherical harmonics, like polynomials on the sphere, so everything's nice.
Right.
If you use a generic manifold, you don't have any idea what the eigenfunctions are, and the Erdős-Turan estimate becomes, I don't want to say useless, but it becomes harder to deal with. And there is a substitute in terms of Green's functions, which I'll talk about on Friday. So you can use sort of Green function type estimates to replace this Erdős-Turan estimate. But if you want to get constants, right, when do you have an explicit formula for the Green's function? You don't. But you have asymptotics, and maybe that's sort of, well, it's also hard, okay? So I'm not going to lie, it's hard. Manifolds are hard.
Right, thank you very much. So are there more questions?
Can I, yeah, sorry, I just keep asking those silly questions, which are only due to me being late to the talk. So do you know about optimal quantization? So this is the same as the optimal quantization problem, right?
Someone emailed me once and said, this looks like optimal quantization. And then I said, oh yeah, I'm going to look at it. And then I put it on my big pile of to-do things to read that I don't know.
I think this is the optimal quantization problem.
Like how do you round, right? Optimal rounding?
Well, in particular, optimal rounding. Basically, so I think that the statement is just like this. It's literally just the Wasserstein distance from discrete measure to the uniform measure. But one of the things that they do, they show that you can, for example, just integrate the Voronoi cells. So the metric is is equivalent to if you were just in.
Yes, but that's not the sequence problem. That's the set problem, right? If you have a set of points, it's
not exactly. Yes, right. Absolutely.
Right, so the question is then, how do you put the next point? How do you put the next point? How does this depend on things? And
absolutely. Yeah. Mm-hmm.
I mean, actually, I have one paper with Amir Sagi, if you can find this online. And Amir and I had a long discussion about what to put in the abstract, and I was victorious. And there's a line in there that says, if it's easy to buy milk all the time, there are many supermarkets. And so I think all these problems are sort of, they all straight come from real life, right? It's actually transporting mass from A to B, right? I mean, I'm surprised there's no one from the UPS in my talk, right? I mean, that's sort of the scale of real life here. This is real life. This is the mailman sending mail to your house.
Great. So, perfect. Should we perhaps stop the recording to make this video short, and then we can continue with questions later on?